Homework busy? No more. At Spring Library, we explain every topic in simple way. Join the learning family and score high every day.
All right, question 30 is a bit of a long one, but it states, when a nuclear reactor is in a critical state, the neutrons released in each fission trigger an average of exactly one additional fission. If the average number of additional fissions triggered rises above 1, the reactor enters a supercritical state in which the fission rate and the power output grow very rapidly. A reactor in a critical state has a power output of 25 kilowatts, which here I put as P naught or P initial, 25 kilowatts. The reactor then enters a supercritical state in which each fission triggers an average of 1.01 additional fissions. So here I have number of fissions, or N per fission is 1.01. The average time for the neutrons released by one generation of fissions to trigger the next generations of fissions is 1.2 times 10 to the negative 8 seconds. How much time elapses before the power output from a single generation of fissions grows to 3,300 megawatts? So P here, P final would be 3,300 megawatts. So essentially it states that we want to build a model that would kind of represent what's happening here. So essentially we're saying that the power at time, I'll say power 1, equals the initial power, and that this P1, this increase in power, occurs when we have a reaction or a fission or neutron created from fission. And then for P2, if this happens again, we have P1 times N, right? So we go to this next state when we have this other state behind it. But if we substitute in P1 with that equals, that's P naught times N, again times N. And we can continue this pattern forever. So the P at some time, I'll say, I don't know, K. I guess it would be PJ, the letter before that. But then we have N, the number of reactions, to the power, we'll say K, right? Maybe I'll make it a little more clear, just for my writing's a little big. So for N number of fissions, that goes to the power that we're dealing at power K, right? So the scenario, we know P, our final power, and we know P naught, our initial power. And we know the N actually, but we just don't know how many reactions have to occur. I'll call it X in this scenario just as an unknown variable. So how many of these fissions have to be created to go from this initial power to our final power? Since we're given everything in this equation, but for X, we can simply rearrange to solve for X. So here's what we will do. Take the ratio P over P naught. That equals N to the power of X. X, again, the number of fissions that has to occur. You can take the natural logarithm of both sides, P over P naught. Equals X times ln of the number of reactions, we'll call N, and simply the number of reactions that would occur to go from these two different power states, logarithm of the ratios of P over N. And we find the number of reactions that would occur would be 1184.9 events, which I guess we would round up to 1185, let's say. It's hard to have a non-discrete number of events. So we're told we can solve, how many events occur, but we're looking for how much time elapses. But we were told that for one reaction to occur, it's this time value. So we can say that the total time that would occur, total time, we'll call that, I don't know, T tot, would simply equal the number of reactions multiplied by the time per reaction. So X times T, which we can solve. So 1185 times 1.2 times 10 to the negative 8 seconds. And we can find that this power can very, very rapidly increase in a very small time frame of 1.4 times 10 to the negative 5 seconds. So this should show how fast reactors can produce a large amount of power, indicating that these are very powerful systems that obviously need to be controlled very well. So there you go.